Hello everybody, so this is the first video associated with Chapter 2 of the Introduction to Quantitative Finance course. So the objective of this chapter is to present an option pricing methodology for a very simple model based on trees. So it's a simple discrete time model that we will explore in the chapter. And the idea is that we saw in previous chapters that the absence of arbitrage led to bounds on prices of options, but did not specify a unique price. So now what we're going to do in this chapter is we're going to propose additional assumptions related to the behavior of the underlying asset. And then these assumptions will lead to unique possible prices of options. So the model presented in this chapter is maybe overly simplistic, but it will consist in a good building block to build on the intuition and understand more complicated models subsequently, such as the model proposed in chapter 3. So what are the assumptions associated with our model? Well, we'll start with a very simple model, which is a one period model. So we're going to assume that there are two time steps, time 0 or time 1, and that our sample space, this is a probabilistic sample space, has two possible outcomes, either omega 1 or omega 2. So it's as if you tossed a coin. Outcome omega 1 would be head, and outcome omega 2 would be tails. Okay, so there are only two possibilities in this simplified model. And then the probabilities associated with these two outcomes are probability P for outcome omega 1 and probability 1 minus P for outcome omega 2, where the constant P is a constant between 0 and 1. So this here, this stylized P represents the probability measure, which assigns the probability respectively P or 1 minus P to each of such outcomes. In the market we're going to assume that there are exactly two assets that are traded. The first one is a risk-free asset, which behaves a bit like a bank account. So its value grows deterministically at the risk-free rate. So we consider, again, a deterministic risk-free rate, continuously compounded rate, denoted by R, which we assume is greater than 0. And then we're going to assume that the dynamics of this asset is as follows. At time 0, its value is 1, and at time 1, its value is exponential of R. Okay, so the value of this asset is not random, it's deterministic, and it increases from 1 to exponential R between time 0 and 1. Okay, so you accrue interest on one period if you own this asset. The second asset we consider is a risky asset. So the previous asset was risk-free, it was deterministic. Now this one is random and risky. So the second asset, denoted S, we assume it has an initial price at time 0, denoted by S0. We assume its price is greater than 0, so you can think of S as a stock, for example. And we're going to assume that its final price at time 1 is random. Okay, so if outcome omega 1 occurs, then the price of this asset S at time 1 under outcome omega 1 will be S0 times U. So its initial price is multiplied by U. And if the second outcome occurs, the price of the risky asset at time 1 under the second outcome would be S0 times D, where U and D are two positive constants, and U stands for up, D stands for down. Okay, so here typically U represent an upward movement in the stock, whereas D would represent a downward movement in the stock value. So under this model, the movements of the stock price or the risky asset price can be represented by the following tree, where the initial value of the stock is worth S0 at time 0, and then at time 1 there are two possibilities. Either it goes up to S0 times U with a probability P, or it goes down to S0 times D with probability 1 minus P. So one period, two possible outcomes. This is a very simple model, which is oversimplistic, but this simple model will allow us proposing our first option pricing procedure, and we'll build on this first model to make it more complicated subsequently. So now in that market where we have two traded assets, we can set up portfolios to invest in these assets. And the use of portfolios will be critical for the pricing of options, as we'll see subsequently. So we to define portfolios, we have to define trading strategies. So a trading strategy is a couple theta, which consists in theta S and theta B. So theta S will be the number of shares of the risky asset S in the portfolio, whereas theta B is the number of shares of the risk-free asset B in the portfolio. Okay, so these thetas, they are real numbers. They can be either positive or negative or zero. So what do negative values mean here? So theta S is smaller than zero. It means that you sell short the risky asset. You hold a negative amount of asset, meaning that you've sold some which you don't own. Whereas theta B being smaller than zero, this is equivalent to selling short the risk-free asset. But if we think of the risk-free asset as a bank account, it means that you borrow some money. Okay, so theta B greater than zero, it's as if you lended some money, and theta B smaller than zero, it's as if you borrowed some money. So you owe that money to somebody. Okay, you have your asset is negative in that case because you're in debt to someone. So based on this trading strategy, we can define what we call the portfolio value at time t. So here VT theta stands for the portfolio value at time t for the trading strategy theta. This is defined as theta S times ST plus theta B times BT. So the value of the portfolio at time t is the number of shares of the risky asset in the portfolio times the risky asset value at time t plus the number of shares of the risk-free asset times the price of the risk-free asset at time t. Okay, so we define trading strategies, which is the composition of a portfolio, and we define the portfolio value from that trading strategy. Okay, so we said that the stock price can go up or down. If it goes up, its price is multiplied by U. If it goes down, it's multiplied by D. But one question we might ask ourselves is, what are values which make sense for R, U, and D? Are there values which we should rule out? And by making sense, I mean, can we ensure that for a given set of values R, U, and D, there's no arbitrage on the market? Okay, because if our model admits arbitrage, it doesn't really make sense for option pricing. Okay, because it means that in this market we can make some amount of money for free without taking any risk. So this doesn't make sense. So we will want to rule out models where there are arbitrage strategies. And the following proposition gives an answer to this question. It says that in this market, there are no arbitrage strategies if and only if we have the following relationship. U must be greater than the exponential of the risk-free rate, which must be greater than t. Okay, so this is the result we're gonna prove subsequently. Okay, so then let's prove the result. Okay, so we want to show that this must hold to prevent arbitrage. So first we're gonna see what happens if this inequality doesn't hold. Okay, so the first violation of the inequality from the proposition would be if exponential of r is greater or equal than u. Okay, so what happens in this case? So because the proposition said that this value exponential of r should be in between d and u. So now we're going to assume that it's greater than or equal to u, and we're going to see what happens. So in that case, we're going to see that there exists an arbitrage opportunity, which is obtained through the following trading strategy. Okay, so we're going to sell short 1 unit of the risky asset price, and we're going to hold S0 shares of the risk-free asset. What happens in this case? So under this portfolio, what is V0, the initial value of the portfolio at time 0? At time 0, by the definition of V0 is the number of shares of stock times the initial stock price plus the number of shares of the risk-free asset times its initial value. Okay, and recall that here theta s we defined it as -1, so this is minus S0. Theta b, it is equal to S0 by our assumption, and B0 we said it's equal to 1, so this is minus S0 plus S0, which is equal to 0. So this portfolio indeed has a 0 initial value, and then we're gonna look at what happens at time 1. So the value of the portfolio at time 1, it is the number of shares of the stock times the risky asset value at time 1 plus the number of shares of the risk-free asset times its time 1 value. So here we said that theta s is -1, so this is minus S1. And here this is S0, and this is exponential of r, so this is S0 exponential of r here. So here we said that S1 can be either S0u if we have an upward movement, or S0d if we have a downward movement in this stock. Okay, so if the outcome omega1 occurs, then the stock has an upward movement. S1 is replaced by S0u, and the portfolio value is given by this guy at time 1. Conversely, if there's a downward movement in the stock, S1 will be replaced by S0d, so this portfolio value can be written as this quantity here if we factor out S0. Okay, but then by our assumption, exponential of r was greater or equal to u, and u is strictly greater than d. So it means that this first quantity here, it is greater or equal to 0, and this second quantity here, it is strictly greater than 0. So in that case, it means that the probability that the portfolio value at time 1 is greater or equal to 0, this is the probability that either outcome 1 or 2 occurs, because we saw in both cases these are greater or equal to 0, which is 1. So you're certain at time 1 that your portfolio will be worth at least 0. Furthermore, are there scenarios where the portfolio value at time 1 is strictly greater than 0? The answer is yes. So for outcome 2, we had by assumption that exponential of r is greater than d. So this portfolio value under outcome 2 would be strictly positive. So the probability that the portfolio value is strictly positive at time 0 would be greater or equal to the probability of outcome 2. And this one is greater than 0 because this is 1 minus p. And furthermore, I forgot to write that previously, but we assume that 1 minus p is strictly greater than 0. So p is smaller than 1. So then this probability is greater than 0. This means that the portfolio here, because it's always greater or equal to 0 at the terminal value, and we have a positive probability that it is greater than 0, and finally its initial value is 0, because of all these three conditions, this is an arbitrage opportunity. Okay, so this contradicts our original assumption we're making when we price derivatives, that there's no arbitrage on the market. So for this reason, we saw that if this happens, so if exponential of r is greater or equal to u, then there are arbitrage opportunities on the market. Then we're going to study a second case, which is analogous to the first one. So I'll go a bit quicker on this one because the steps are pretty much the same. But now we can investigate what happens in the second case, which is if the exponential of r is smaller or equal to d. So instead of being greater than d, what happens if it's smaller or equal? Then again, we can identify an arbitrage opportunity through the following steps. Okay, so here, intuitively, we can see that because u and d are greater or equal to r, exponential of r, then the stock return will always be greater or equal to the return of the risk-free asset. So what can you do in that case? You can hold the stock because it always has a higher return, and you can sell short the risk-free asset because it always has a lower return, and then you construct an arbitrage opportunity from this. Okay, so under this strategy here, where you hold 1 share of the stock and you hold minus 0 shares of the risk-free asset, the initial portfolio value here is given by V0 is theta S, so this is 1 times S0. Okay, so this guy is S0, plus theta B, this is minus S0 times 1. So the sum here is S0 minus S0, which is 0. So this portfolio indeed has an null initial value. And furthermore, at time 1, we can use the definition of the portfolio value, which is theta S, S1, number of shares of the stock times the stock value at time 1, plus number of shares of the risk-free asset times its value at time 1. And here we said that, okay, so this is 1, so this is S1, and here B1 is exponential of R, theta B is minus S0, so we obtain this quantity here. And again, we can study the two cases. So S1 can either be S0U if the stock price goes up, or S0D if the stock price goes down. So the two possible values at time 1 for the portfolio value are these. Okay, so under our assumption, we had that both U and D were greater or equal to exponential of R, and the inequality was strict for U. Okay, so both these terms are greater or equal to 0, but this first quantity here is strictly greater than 0. So for that reason, the probability that the portfolio value at time 1 is greater or equal to 0, it is 1, because in both scenarios you have the portfolio value greater or equal to 0. Conversely, if you look at which scenarios lead to a final portfolio value strictly greater than 0, then this contains at least the first scenario here, because we said that U is greater than exponential of R, strictly greater. So for that reason, this quantity is strictly greater than 0. So for scenario 1, you're certain to have the portfolio value strictly greater than 0. So this probability, it's P, which is greater than 0. Okay, so we see that this portfolio we've set up is an arbitrage opportunity under that assumption. Okay, so we saw that if either exponential of R is greater or equal to U or smaller or equal to D, then we do have arbitrage opportunities in the market. Okay, so we've proved the first part of the previous proposition, and now what's left to show is what happens in the third case when U is greater than exponential of R, which is greater than exponential of D. Okay, so we have to show that in this case, then uh, there exists no arbitrage opportunity on the market. Okay, so to have an arbitrage opportunity, you need to have a portfolio value which is 0 initially and greater or equal to 0 at the end with a positive probability of being greater than 0. So the first condition entails an initial portfolio value which is 0. So if we have a portfolio value which is 0 initially, it means that, okay, maybe I'm going to write this. It means that theta b 0 is equal, oops, sorry, okay, plus, this is a plus sign, plus theta S0 is equal to 0. So initial portfolio value is equal to 0. And this guy here, the B0, this is equal to 1. So if you isolate theta B here, this entails that theta B is equal to minus theta S S0, which is the equation above. Okay. So if we want to have a candidate for an arbitrage opportunity, then the composition of the portfolio must satisfy this equation. So then let's look at the portfolio value at time 1. By definition, the portfolio value at time 1 is equal to theta S S1 plus theta B B1. But then what we can do is we can substitute the theta B by minus theta S as 0. So if we do that, we can factor out theta S, and this gives theta S S1 minus a 0 exponential of R. This exponential of R is the value of B1 here. Okay, so here S1, again, it can be expressed as either S0U if there's an upward movement, or S0D if there's a downward movement. Okay, so here the final portfolio value in both under both outcomes are given by this equation here. Okay, so if this is the value of the portfolio at time 1 that we've considered above if there's an upward movement in the stock, and here this is the value of the portfolio in the second possible outcome if there's a downward movement of the stock. And we can see that here the sign, okay, there are two cases. Either theta S is equal to 0, so in that case you invest nothing in your portfolio and the portfolio value at time 1 is always equal to 0. Okay, so if theta S is equal to 0, then the portfolio value at time 1 is always equal to 0. So there's a 0 possibility for profits, so clearly this is not an arbitrage strategy. Conversely, second case is what happens when theta S is greater than 0. So if theta S is greater than 0, then this second expression here, it is strictly negative. Okay, so D is strictly smaller than the exponential of R. So this last expression for outcome 2, it's strictly negative. So because of that, this portfolio is not guaranteed to not lose money. So it's not an arbitrage opportunity. Okay, so the probability that V1 is strictly smaller than 0 is equal to the probability of omega 2, which is strictly greater than 0. Okay, because we assume that P is strictly smaller than 1. So in that case, again, the portfolio is not an arbitrage opportunity because it can lose some money. And then finally, in the last case, if theta S is smaller than 0, then that first term, so this is negative, and this is positive, this is positive. So this value here, which is the portfolio value under an upward movement of the stock, would be negative. So again, in that case, the probability to have a negative final value of the portfolio at time 1 is the probability of omega 1, which is p, which is strictly greater than 0. So again, the portfolio is not an arbitrage opportunities. So we've seen that for all portfolios under this assumption, for all portfolios, if the initial value is 0, then this must be satisfied, and this equation implies that there's always a positive probability of losing money unless the portfolio is 0 all the time. But this is not an interesting case. Okay, so if theta s is equal to 0, then you have 0 possibility of gain, so there's no arbitrage opportunities. And if theta s is different than 0, then there's at least one of these two terms which is negative, so the portfolio is not an arbitrage opportunity. And this completes the proof. So we've just shown the last case. If exponential of r is in between d and u strictly, then there's no arbitrage opportunity on the market. Okay. So now what we're going to do, we want to do some option pricing. So what we're going to do, we're going to add a new derivative or a new financial instrument to the market. And we're going to assume that its payoff at time 1 is random and is denoted by C1. Okay, so C1 is a random variable which can be worth two different values, one in state 1 or outcome 1, one in state omega 2. So the question we might ask ourselves is, if there exists some new financial instruments whose payoff is C1 at time 1, what would be possible prices C0 at time 0 for this derivative? And what do we mean by what possible price? We mean what are the prices which would preclude arbitrage opportunities. Okay, so in practice, we said arbitrage opportunities, when they exist, they tend to disappear shortly. So it makes sense to assume in our model no absence of arbitrage opportunities. And under the absence of arbitrage, then we can try to deduct what should be the price of the derivative. Okay, so we are going to try to find a price C0 of the derivative or the option at time 0, which precludes the presence of arbitrage opportunities in our market. So how are we going to do that? We're going to exploit what we referred to as the law of one price in the previous chapter. So we're going to try to find a portfolio whose terminal value is equal to the option payoff almost surely. So almost surely means with probability 1. So we're going to find a portfolio whose final value at time 1 is always the same than the payoff of the derivative. And if both the portfolio and the derivative, they have the same payoffs, then they must have the same prices by the law of one price. Okay, so this would entail that the price of the derivative should be the same than the price of that portfolio. And this is the strategy we're going to use to price the option in that context. So in other words, what we've just said is, if we can find a portfolio whose terminal value or whose payoff is always in all scenarios equal to the payoff of the derivative, then the initial value of the portfolio or its initial price should be equal to the initial price of the derivative. Okay, so this would specify the price of the derivative, which would be the initial value of the portfolio. Okay, so just a bit of notation here to make the notation lighter. So here C1 omega 1, which is the price of, the payoff of the derivative in under outcome omega 1, we're going to denote it by Cu, which means that this is the payoff of the derivative when the stock price goes up. And C1 omega 2 is the derivative payoff when the stock price goes down. Okay, so we're going to denote it by CD here. Okay, so CU and CD are respectively the derivative payoff when the stock price goes either up or down. So here, theorem, in our binomial model with two states, the following portfolio, which we call a replicating portfolio, has the following property. It has that C1 is equal to V1 with probability 1. Okay, so this portfolio, which we will define shortly, has the feature that its final value here, it's always equal to the value of the derivative at time 1 for all scenarios. And how do we define this portfolio? This portfolio is as follows. So the number of shares of stock in the portfolio is defined as CU, so the derivative payoff in the upward state minus the derivative payoff in the downward state, divided by S0 times U minus D, which are respectively the increase or decrease factors for the stock price in both outcomes. And here theta B here can be defined as UCD minus DCU divided by B1. So this is exponential of R times U minus D. Okay, so this is a theorem, a result. Now we can prove it. Okay, so what this says is that we haven't proven it yet, but once we're gonna prove it, this is gonna show that in our market, for any derivative C1, there exists a portfolio whose composition depends on the payoff of the derivative in both states. But for that portfolio, the final value of the portfolio will be equal to the payoff of the derivative with probability 1. Okay, so this is why we call it a replicating portfolio. It's because the final value of the portfolio replicates the payoff of the option. It always has the same value. So proof. So how did we come up with these equations here? This is obtained as follows. Okay, so we're seeking a portfolio for which its value in the state under outcome 1, if the stock price goes up, must be CU, the payoff in outcome 1. And we want that the value of the portfolio under state 2 is CD, the payoff of the derivative in under outcome 2, so a downward movement of the stock. So here we can recall the definition of V1. So recall V1 is equal to theta B1 plus theta S1 here. So this we can replace V1 by its respective values here, CU or CD, and this gives a system of two equations. Okay, so here the first equation here is the first line of this matrix equation. So here CU, the portfolio value, must be equal to the portfolio value at time 1, and portfolio value at time 1 can be written as B1 times theta B plus S1 omega 1 times theta S. So this is the risky asset price in state 1. And here the second equation here is simply the second line of this matrix equation, which is CD, option payoff or derivative payoff in the downward state, must be equal to the portfolio value in the downward state, which is B1 theta B, plus the stock value in the downward state times the number of shares of the stock value here. Okay, so this is a system of two equations, two unknowns, where the unknowns are theta B and theta S, the composition of the portfolio. So you can solve this system of equation. I won't do it here, so I encourage you to pause the video here and solve this system of equation by yourself. But this is two equations, two unknowns, so it's not very difficult. And once you do that, then you can get to the following solution here, which is theta S is equal to this quantity, theta B is equal to this quantity, and this is the portfolio we've proposed in the previous slides. Okay, so this is how we came up with this composition of the portfolio. This composition is obtained by setting up V1 is equal to C1 in both states, either the upward state or the downward state. And this guarantees that the portfolio theta, which consists in this allocation to the stock and the risky asset, always has a value at 1 which is equal to the payoff of the derivative in both respective states. Okay. So then we've identified a replicating portfolio. Then to price the option, the only thing that remains is to find what's the initial value of the portfolio. Because we said the initial value of the portfolio we've identified must be equal to the initial price of the option through the law of one price. So we're going to see that the initial value of the portfolio has the following representation. So here we're going to see that the initial value of the portfolio is the discount factor, exponential of minus the risk-free rate, times the expectation of the payoff. But here the expectation is not under the physical measure P from the beginning of the chapter. It's under a fictitious probability measure that we are going to call Q. So which assigns the probability, the following probability to omega 1, the first outcome, and this probability to outcome 2. Okay, so Q, it's not a real probability measure. It doesn't reflect the real probability that the stock price goes up or down. It's just a fictitious probability measure that is useful for calculations. And we can notice that these can indeed be probabilities because these two guys here, they're both contained between 0 and 1. And if you sum both these probabilities here, you can do it yourself. So pause the video for 2 seconds and sum these probabilities. You can see that the sum is equal to 1. Okay, so this Q here, defined through these probabilities, is indeed a probability measure because it leads to probabilities associated to both outcomes being between 0 and 1 and probabilities summing to 1. Okay, so now let's show this result to show that the initial portfolio replication portfolio value has this representation here. Okay, so proof from the definition of V0, then we have this result. So the definition of V0, the initial value of the portfolio, is the number of risky asset shares times the initial value of the risky asset plus the number of shares of the risk-free asset times the initial value of the risk-free asset. So this is equal to 1. And here we can replace theta S and theta B here by their respective values. So here theta S and theta B will go back a few slides. We can take here these values, copy them, and here paste them here instead of theta S and theta B. Okay, so this is just substituting theta S and theta B from the last theorem here. And then if you do that, you obtain this quantity here. So again, here I don't have a blackboard to write, so I again encourage you to stop the video at this point and make that substitution yourself to ensure that you obtain here this quantity. And then please continue and again stop the video and rearrange the terms so that you obtain the second equation here. Okay, so here you can go from here to here just by rearranging the terms. And here you can see that this guy here is what we defined as the probability of state 1 under the probability measure Q, under the fictitious probability measure Q. So this guy here, we called it Q omega 1, and this guy here, we called it Q omega 2. Okay, so here B1 is the exponential of R, so you can take this guy, plug it, and see that this guy here is indeed Q of omega 2. Okay, so here, this shows that, maybe I'll write it, V0 is equal to exponential of minus R. So we can factor here, this exponential of R, we can factor it out, and this gives Cu times the Q probability of omega 1 plus CD times the Q probability of outcome 2. So here this gives V0 is exponential of minus R times this guy. This guy is simply the expectation of the payoff, but under the probability measure Q instead of under the physical measure. Okay, so these Q probabilities, they're not P and 1 minus P. They're defined in terms of values D, U, and exponential of R, which are the constants driving values for the assets in both respective cases. Okay, but this gives the following representation. It says that V0, the initial replicating portfolio value, can be expressed as the discounted expected payoff of the underlying asset, not under the true measure P, but under some fictitious measure Q, defined as follows for convenience purposes. Okay. So here in that slide, initial value of the replicating portfolio is the expected discounted payoff of the derivative under Q. But here recall we said that because V is a replicating portfolio, this initial portfolio value must be the initial price of the option. So this shows that under this binomial model, the initial price of the option, or it can be any other derivative whose payoff is C1, its price is C0 and is given by the following relationship. Okay, so the price of any financial instrument or any derivative in that market is given by the discount factor times the exponential of the payoff of the derivative, but the exponential, the expectation is not under P, so probabilities are not P and 1 minus P, but these probabilities under the Q measure were defined artificially according to this this equality here. If we go back here, it's this equality. Okay, so for those who did some life insurance classes, this is somewhat reminiscent of what you do to price life insurance contracts. So the price of a life insurance contract, it's the expected discounted payoffs from that contract, but here there's a key difference. In your life insurance contract class, the expectation is under the true physical measure, whereas here in the quantitative finance class, this expectation is taken under the risk neutral probability measure. Okay, so why is that the case? This can be a lengthier discussion, but the reason is that here in the finance class, we can replicate the portfolio, we can replicate the payoff of the derivative with a replicating portfolio. Okay, so in your life insurance, there's no such replicating portfolio to replicate the payoff of the life insurance contract. So this is why we have a different paradigm here in the financial mathematics class and in the life insurance class. It's because in life insurance, there are no replicating portfolios for the payoff of a life insurance, whereas here in financial mathematics, we can find some replicating portfolio, and this explains why we can use a risk neutral measure instead of a physical measure. Okay, so sorry. Here, the fictitious measure, I called it a risk neutral measure. Okay, and why do we call it risk neutral measure? It's because this measure allows us to obtain price of derivatives simply by taking the expectation of its payoff and discounting at the risk-free rate. So because under this measure, the discount factor to price derivative is the risk-free rate, then this measure Q is often called a risk-neutral measure. Okay, so in a nutshell, it's called a risk-neutral measure because under that measure Q, we can price derivatives simply by calculating the expected payoff discounted at the risk-free rate. Okay, so risk-neutral means we can discount at the risk-free rate. So we're going to stop here. So we've presented the case for one period. Now in the next video, we'll extend this binomial model to the case of multiple periods. So thank you. Have a nice day.